Hello, my name is Pablo Solé, and I will be speaking about attacking embedded languages. Well, first of all, I'm a security researcher in Immunity. My major job is research and do some development of client-side exploits for the Canvas attack framework, and doing some custom binary analysis tools. Thanks. Thanks for that. Because I'm part of the Immunity Debugger developer team, so that's most of all what I do. First of all, we will start speaking about some introduction and background of embedded scripting languages. And we use two different PDF display tools as a case study, the Acrobat Reader and the Fuzzers Reader. And then we use Immunity Debugger to decode some JavaScript objects, some properties, methods, and some arguments. And using this information, we'll do a Spike script, which is a fuzzer language. And we will finish showing how to find and exploit already patched bugs, which is the collectmail info bug. First of all, vulnerability assessment is becoming a really specific task because the generic fuzzers, the blind fuzzers, and the source analysis tools are already used by the vendors itself in his testbeds. So we can't use the same tools here for attacking. So we have to create application-specific tools to get into the structures behind the things that a blind fuzzer can really find. So we create an Immunity Debugger to achieve this task. And we add a Python scripting language inside and a complete library to help the static and dynamic analysis. So we have to create this reverse engineering scripts using this Immunity Debugger library, which uses itself the core Immunity Debugger. So this kind of application we will see now are almost like browsers. They have user interaction, they have plugins, multimedia access, all that, the same thing that you can get in, and of course scripting, all the same thing you can get in a browser. So recovering interesting and important information about the works, how it works, and how the JavaScript information is stored inside the application is really complex. The data flow is really complex inside. So we made this analysis tool that allow us to get inside of the JavaScript core and inside the plugins and inside the binary objects. So we can get information from each of its parts and mix them to do a real nice fuzzer. Bugs, kind of bugs that you will find in this application are sandbox escaping. Inside a JavaScript script, inside a PDF document, you are inside of a sandbox. You can't access the complete API. You just access a restricted section. Other kind of bugs you will find is object initialization. You have double freeze and all the kinds of JavaScript object initialization bugs. And there's also buffer overflows inside of the native methods and also some shellscape bugs. This is a fertile ground to research because, as we said before, you need very specialized tools to get across the scripting level. And you have to mix the binary level and the JavaScript level to get all the picture. And sometimes the team making the JavaScript or Visual Basic, whatever scripting engine, is different from the team doing the rest of the application. So sometimes there's some kind of lack of communication between both teams, and there's some bugs there. And also the data flow is really complex to follow because all these are big, huge objects, with I don't know, tons of function tables and that stuff, and it's really painful. So first of all, this case of study. Adobe's implement an HTML script engine, which is a kind of standardized JavaScript engine. And inside Adobe's, all the JavaScripts are executed as a response to a particular event. So when you open a document, when you open a page, when you click a button, there's just your chance to put some JavaScript. Here we have some examples. And each event is a tuple. You have an event type, which is application, batch, console, document, page, menu, and you have name, init, etc. So each event type defines a security context. You have the document security context, the application context, and so. And so you have two levels of privileges. We have privileged contexts, which are the application level context, so on the batch and console events. And you have the non-privileged context, which is almost everything else. Everything you can touch from a document is non-privileged. So you don't have access to the complete API. Well, and you can raise, of course, your security context creating a trusted function. But to create a trusted function, you need to be in a privileged context. So it's not an option in the way of an attack. So the first kind of threat that you can find is breaking non-privileged sandbox. Rather show how to break a sandbox using the check for date function, which is an undocumented function. These functions raise its own privileges, and then it calls a user-controlled callback. So this user-controlled callback function is under a privileged context and can run everything. There's an example where we define my callback function, which is user-controlled, and you call a new doc function, which is the privileged, and then we call the check for date using the oCallback argument and set it to my callback, the function we created before. Also, there are some overflows in built-in functions. There's a Stack Overflow in the collect email info function, which is undocumented also. In the message argument, you can override the complete stack. And we'll use this collect email info back as an example later. And also, there's an extensive undocumented AIP. These undocumented functions tend to receive less testing because they're for internal use. So, well, as an example, the collab object inside the Adobe Acrobat Reader's AIP has only 3 documented methods and no properties at all, when it actually has 48 members. That's a lot of non-documented functions. So, some examples. As part of the initialization process, Adobe Acrobat Reader registers a series of JavaScript objects. These JavaScript objects are just containers for different properties and methods or many other objects. And, well, a property has 2 associated functions, which is a getter that you use to get the proper value, and a setter. This is used when you want to change some proper value. Also, methods have one associated function, which is what you execute when you call the method. An object has a constructor function, which is executed as part of the instantiation process. The first we see is in the eScript plugin, there's a static list of objects that sets his properties here. You have first a pointer to the object's name, in this case it's APP, and then you have a pointer to an array of members, and there's a counter, there's 52 hexadecimal members. And then you have this is the structure for each member. I use a browser doc method as an example. You have the pointer to method names, and you have a pointer to a security structure that we see now. This security privileges structure sets the allowed method events, where you can execute this method. In this case, the browse-for-doc method, you can execute it only in the application initialization and console execution events. So if you try to execute this restricted method inside at least, a document open, it's not going to work. No. This is just a summary I put here in case you want to, to try something someday. Also, each plugin associates function pointers to each method. You have here the collect email info registering, which is pointing to an internal function, a native function, and also do the same for the property getters and setters. We have here the default store property. This is the setter and the getter for the default store property. And also some methods set some security restrictions inside the function itself. How they make this? They make a list of allowed events runtime and compare it with the executing event. And that's how they decide if you can execute or not that method. Well, every method's call is made from a single dispatcher. Here, the last instruction is a call to the real native function and pass as arguments the function names and a JavaScript object that has an array of arguments. So all the JavaScript arguments that you see there are passed as a pointer to the function. And also inside each method, there's a generic argument parser. Each method that you call expects the argument in a very specific format, and this format is here. This argument parser structure says first the name of the argument, in this case is 2. The type of the argument is the bool, integer, or whatever. In this case is 6, which is a Unicode string. Then you have flags. In this case, this is an optional argument. And you have the buffer, which is set by the parser itself. So after the parser executes, you get the buffer that you used in the JavaScript inside your binary structure. And you have this used field, which is set by the parser if the argument was correctly parsed. Well, Foxy Reader use almost the same approach of registering their objects and methods and properties runtime as part of the initialization. But here the arguments are checked manually. So you don't have a central argument parser. Each method re-implement the argument parser. But you have a central dispatcher for all the methods called as in the addobs. Okay. Here we see how to register a new object. The last argument is the object name. How to register a new property. You have the setter function, the getter function, the property name, and the parent object. This parent object is the object identifier that we get here. So you first here get an object identifier that you use here, and you use here when you register a new method. A new method needs how many arguments this method are expecting, also the function pointer, the function name, and this parent object. And here you have the method called dispatcher. So this dispatcher sends the arguments arrays and the arguments counter to the real function that is going to execute our function. This is an example of a decoder I made using Immunity Debugger, which show all the registration process when you register all the methods or the properties and whatever. You have there, I don't know, the function pointer for the getter, for the setters, for the methods, the argument counters, etc. So we'll try to decode all this Adobe JavaScript engine using Immunity Debugger. We have two approaches to do this. We have static analysis and dynamic analysis. And the static analysis approach is going to try to decode all these structures we saw before, trying to get the object names, the methods and property names, and the security privileges. This is an example. This is all Python using the Immunity Debugger library. First, we read the pointer to the object name. Then we read the strings of the object name. And we have the pointer to the members and the member counters. This is all Python. Then we decode the member structures. Always it is the same way. You get the pointer to the member name, you then get the name and all the structure. Here we get the allowed events array, which is this. This is application initialization and bash execution. This is another one. This is another snapshot that's doing all this in an automated fashion. And well, in the dynamic approach, we put some hooks on the method dispatcher and the argument parser. Here, hooks is a breakpoint that allows us to execute a Python script. Inside this Python script, we can control everything of the program state. We can read the register state, we can change the memory, whatever we need to do and using Python. That's awesome. And we created an extensive API for all this, which is called Immunity Debugger Library. And we have a heap library, a control data flow library, lots of tools to help and to assist this dynamic analysis. So we put some hooks on methods dispatcher, just in the call instruction. And the stack, the second keyword of the stack is our function name. So putting this hook, we know exactly what is getting executed in the application. If you try to put this hook on the application initialization, you see that Adobe itself executes tons of JavaScript methods that you never know. Well, this is the script itself. We have this method called hooks, which is a class, or a Python class. We get the ESP value, then we get the string from there. And we do just a print in the log window. We have this hook in the argument parser. We have to put our hooks in the parser itself at the end of the function, so we get all these buffer and usage field actually filled with the information that's going to get into the real function. So this is how you see the argument parser call, and this is the script itself. You can decode the name of the argument, the type, and the most important part, you can get the buffer that is going to get executed by the function, and if some argument is used or not. We have an example. Here we have a call to the collectML info function, and well, this is actually a snapshot of the exploit of the collectML info bug. Fuzzing with the spike. First, using this static approach, we get a list of all the methods we can execute in the Adobe JavaScript. And then using the dynamic strategy, we get all the arguments of each method. And finally, we can fuzz each argument because we know the type of the argument using Spike and do a huge JavaScript that fuzz every method. So we get all the methods, and we make a PDF file calling each function to get all these arguments in a try-catch statement block. And then we attach to Immunity Debugger. We execute this Python hook to get the argument parser stuff. And then we make a spike script like this, fuzzing all the ASCII or Unicode strings. And we get something like this. And this is obviously, this is automated generally. And the collect email info bug. Using this fuzzing strategy, we can find these bugs. We put our hook in the registering function. We execute the collect email info method, so we get this argument. We fuzz each argument. Well, this method opens a new window for each successful execution. So you need some Python or whatever to close automatically these windows. And this is the snapshot of the function that is actually failed in the Acrobat reader. At the beginning, it allocates 2,000 hexadecimal bytes to put the buffer there. But then it checks the boundaries as 2,000 Unicode charts. So that's wrong. You can overflow 4,000 bytes of memory and not just the allocated 2,000. So you can override the safe exception handler with an arbitrary value. That's what we did in the exploit. And heap spread all the memory with our shellcode. So when the safe when the safe exception handler changes its procedure, we get execution. This is a proof of concept of this. We said here we first heap spread with our int3 shellcode, and then we overflow the collect email info function. Okay. Well, some conclusions. Embedded JavaScript engines are very fertile ground yet. The data flow is really painful to follow, so there's not many tools useful, and there's not many works done in this area. And blind fencing is not an option because the vendor itself is using this kind of fuzzing, so it's not an option at all. Well, Immunity Debugger has tons of tools, of scripts already done for this kind of jobs, of tasks. And, well, I think that's all. Thank you for the time. Well, if you have some question, this is the moment. Yeah.
What's Untitled version 2 is out? How many people will you be releasing versions reliability based on that rather than 1.1?
No, it's a different branch. It's all debugger. It's our debugger. We already changed tons of things inside, so it's not matchable. Okay. Okay. Well, thank you for your time.